Looking up at the night sky, seeing all those stars, thousands visible to the naked eye, billions more through telescopes. There's something profoundly unsettling about it. Realizing that every single one is fundamentally unreachable. Not difficult to reach, not expensive, not just beyond our current technology. Actually, genuinely, permanently unreachable in any practical sense. We are trapped in the solar system, as surely as if we were at the bottom of a well so deep no rope could ever be long enough to climb out. And look, I know that sounds defeatist. I can already hear the objections forming. Asterisk, what about Project Starshot? What about generation ships? Warp drives? Or wormholes? Or other exotic physics? What about Voyager already in interstellar space? Asterisk, we'll talk about all of those because the details matter and the reasons they don't work are actually fascinating. But first, I want you to really grapple with a fundamental reality. The distances between stars, combined with the laws of physics as we understand them, create barriers that aren't just formidable. They're essentially insurmountable for any civilization made of biological beings with finite lifespans and finite resources. The solar system is our prison. The sun is the center of our cage. And the bars of that cage are made not of steel or energy fields, but of something far more fundamental. The structure of space-time itself, the finite speed of light, the enormous energy requirements of relativistic travel, and the brutal logistics of keeping fragile biological organisms alive for timescales that dwarf civilizations. Let me take you through this carefully because understanding why we're trapped requires understanding several interconnected factors. The sheer scale of interstellar distances, the physics of propulsion and energy, the biological constraints of human lifespans and psychology, the engineering challenges of building vessels that function for centuries or millennia, and the economic reality that makes interstellar travel not just difficult, but functionally impossible for any society that must allocate finite resources among competing priorities. Let's start with the distances because I think most people genuinely don't grasp the scale. The closest star to our sun is Proxima Centauri, part of the Alpha Centauri system, about 4.24 light-years away. That's the nearest star system, the closest possible destination beyond our own. And 4.24 light-years might not sound like much. Light travels that far in just over 4 years, right? How hard could it be? But here's what that distance actually means. 1 light-year is roughly 9.5 trillion kilometers, or about 6 trillion miles. So 4.24 light-years is about 40 trillion kilometers, 25 trillion miles. To put that in perspective, if you drove a car at highway speed, say 100 kilometers per hour, continuously without ever stopping, it would take you about 46 million years to reach Proxima Centauri. If you flew in a commercial airliner at 900 kilometers per hour, it would take about 5 million years. If you traveled at the speed of the fastest spacecraft we've ever built, the Parker Solar Probe, which hits about 700,000 kilometers per hour, it would still take roughly 6,500 years. Let me say that again. Using the fastest spacecraft we've ever built, reaching the nearest star would take longer than all of recorded human history. The Parker Solar Probe, launched in 2018, would arrive around the year 8,500, assuming it were headed that way, which it's not. The ancient Sumerians were inventing writing around 3,200 BCE, about 5,200 years ago. A trip to Proxima Centauri would take longer than the entire span from the invention of writing to now. And that's just to the nearest star. Most stars are much, much farther. The next nearest after Alpha Centauri is Barnard's star at 6 light-years. Then Wolf 359 at 7.8. The nearest sun-like star is Tau Ceti, about 12 light-years away. The center of our galaxy is 26,000 light-years away. The nearest major galaxy, Andromeda, is 2.5 million light-years away. The observable universe extends about 46 billion light-years in every direction. We live in a universe where the typical distance between interesting objects, stars, galaxies, anything we might want to visit, is measured in light years, but our typical speeds are measured in tiny fractions of the speed of light. It's like being an ant at the bottom of the Grand Canyon, being told there's interesting stuff at the top a vertical mile away. Sure, it's theoretically possible for the ant to climb out, but the scale mismatch between the ant's capabilities and the distance makes it functionally impossible. Now, you might think, okay, but we can build faster spacecraft. We can accelerate to a significant fraction of light speed, right? What's stopping us from building a ship that travels at, say, 10% of light speed? Then the trip to Proxima Centauri would only take 42 years within a human lifetime. That brings us to the second fundamental barrier, the physics of propulsion and energy. Accelerating a spacecraft to even a modest fraction of light speed requires absolutely staggering amounts of energy. Let me give you some numbers. Imagine a spacecraft with a mass of 10,000 kilograms, about the mass of the Voyager probes, which is actually quite small for something needing to support humans or even sophisticated equipment for an interstellar journey. If you wanted to accelerate it to 10% of light speed, 0.1 c, or about 30,000 kilometers per second, the kinetic energy required is approximately 4.5 times 10 superscript 1 joules. How much energy is that? The total energy consumption of all human civilization in a year is roughly 6 times 10 superscript 2 joules. So accelerating a 10-ton spacecraft to 0.1 c requires about 7.5% of humanity's total annual energy production. And remember, that's just to accelerate it. If you want to slow down at your destination, which you probably do, unless planning a flyby, you need the same amount of energy again to decelerate. So now we're talking about 15% of humanity's annual energy production just to send a 10-ton probe. But it gets worse. A 10-ton spacecraft is far too small to support humans for a 42-year journey. A minimal life support system, food, water, radiation shielding, power, scientific equipment. You're looking at hundreds of tons minimum, probably thousands for any reasonable crew and comfort. Say you brilliantly miniaturize everything down to 100 tons. Now you need 10 times the energy, 150% of humanity's annual energy production, just for acceleration and deceleration. And we haven't even talked about where that energy comes from or how it's converted into thrust. Current rocket propulsion works by ejecting mass at high velocity. The problem is to carry enough fuel to accelerate to 0.1 c, you need vastly more fuel than spacecraft mass, which means you need even more fuel to accelerate that fuel, and so on. The rocket equation tells us the mass ratio increases exponentially with desired velocity. To reach even 0.1 c using conventional chemical rockets, you need a mass ratio of something like 1/0, more mass than exists in the observable universe. Chemical rockets are obviously not going to work. So what about other methods? Nuclear propulsion is more efficient. Project Orion, proposed in the 1950s, envisioned a spacecraft propelled by nuclear bomb explosions, literally dropping bombs behind and riding the shock waves. It could theoretically achieve maybe 5% of light speed, but would require thousands of bombs, create massive radioactive fallout, violate treaties, and still take 85 years to reach Proxima Centauri. Ion drives, which accelerate charged particles, are efficient but produce very little thrust. Acceleration is extremely slow. Current ion drives would take decades just to reach speeds that make interstellar travel somewhat feasible, and they still require large amounts of energy. Nuclear fusion rockets, if we could ever build them, could potentially be more efficient. Fusing hydrogen or helium converts a small percentage of mass into energy via E=mc². This could theoretically reach maybe 10% of light speed. But we don't have working fusion rockets. We barely have fusion reactors that break even. A fusion rocket powerful enough for interstellar travel is probably centuries away, if possible at all. What about antimatter? Annihilating matter with antimatter gives complete mass-to-energy conversion, the most efficient possible energy source. In theory, an antimatter rocket could reach very high fractions of light speed. The problem: we currently produce antimatter only in tiny quantities, nanograms per year at enormous expense, with no way to store it safely in large amounts. The total antimatter ever produced by humanity would power a light bulb for a few minutes. Producing enough for an interstellar spacecraft is beyond our capabilities by many orders of magnitude. There are more exotic ideas. Laser sails, shining powerful lasers from Earth onto a reflective sail to push a spacecraft, could potentially accelerate it to significant fractions of light speed. Project Starshot envisions using this to send gram-scale probes to Alpha Centauri at 20% of light speed, arriving in about 20 years. This is probably the most plausible near-term approach. But notice what it involves. Not sending humans, not sending large spacecraft, but sending tiny probes that essentially are sophisticated smartphones with sails. They couldn't carry humans, couldn't slow down, would just fly past at 0.2 C. And even that requires building an array of lasers with a combined power of maybe 100 gigawatts, roughly the output of 100 nuclear power plants, focused with extraordinary precision over millions of kilometers. It's an enormous engineering challenge costing tens of billions, only allowing flyby probes, not crewed missions. So the propulsion problem is genuinely formidable. Every method we can imagine either requires impossible energy, impossible fuel, impossible technology, or only work for tiny uncrewed probes on one-way missions. And that's before we consider the biological and psychological challenges of keeping humans alive. Let's talk about biological barriers, because these are often underestimated. Even if we could reach 0.1 C and get to Proxima Centauri in 42 years, could humans survive? First, radiation. In interstellar space, you're exposed to cosmic rays at much higher levels. Over 42 years, radiation exposure would be enormous, causing cancer, degrading cognitive function, damaging DNA. You'd need meters of shielding, which adds mass, increasing energy requirements. Second, microgravity. Unless your spacecraft is constantly accelerating, requiring continuous fuel, or spinning for artificial gravity, requiring large structure, you're in microgravity. We know from the ISS that microgravity causes bone loss, muscle atrophy, vision problems, immune degradation. Astronauts exercise 2 hours daily and still have issues over 6-month missions. A 42-year journey would cause severe physical deterioration without artificial gravity, technically challenging and adding mass/complexity. Third, closed-loop life support. On a spacecraft, you need a near-perfect recycling system for air, water, nutrients, functioning for decades without external inputs. The ISS recycles about 90% of water. Impressive, but not enough. You need to approach 100% efficiency. Any inefficiency means carrying reserves, adding mass. We've never created a fully closed artificial ecosystem on Earth, let alone in space. Biosphere 2 tried with 8 people for 2 years. It failed. Oxygen dropped, CO2 rose, species went extinct. And that was on Earth with experts outside and an exit. An interstellar spacecraft has no safety net. Fourth, psychology. Humans aren't adapted for multi-decade confinement in small, isolated spaces with no escape or rescue. Studies of Antarctic stations, submarines, and isolation experiments show even highly motivated individuals experience significant stress, depression, anxiety, conflict, sleep disorders, and those are situations with an end date and connection to the larger world. On an interstellar journey, you'd be more isolated than any human ever. Earth becomes just another star. Communication delays grow to hours, then days. Eventually, communication becomes impractical. You're completely alone in a small metal can for decades. No turning back. Maintaining mental health would require extraordinary measures, careful crew selection, psychological support, meaningful work, social structures, recreation, possibly pharmaceuticals. Even then, breakdowns and conflicts could jeopardize the mission. And motivation decay. The people who launch might be excited, but what about 10, 20, 30 years in? When novelty wears off, routine is monotonous, destination still decades away, everyone you knew on Earth is dead or elderly, you spent most of your adult life in a spacecraft. How do you maintain purpose? This is why many proposals involve generation ships, spacecraft large enough to support a community over centuries or millennia, with people having children who eventually complete the journey. The problem? They must be enormous to support viable population, genetic diversity, agriculture, manufacturing, a ship massing millions of tons. Accelerating that to even a small fraction of light speed requires astronomical energy, potentially more than human civilization has ever produced. And it must function as a completely closed, self-sustaining ecosystem for centuries, far beyond anything we've demonstrated. There are also social/ethical questions. People born on the ship never chose to be there, stuck on a journey they had no say in, possibly never seeing a planet. Is that ethical? What if later generations decide they don't want to continue? What if social structure breaks down? Now, another fundamental problem: information and control. Once far from Earth, lightspeed communication delays mean any problem requiring Earth-based expertise takes years to communicate, let alone fix. If something goes wrong a light year away, it takes a year for the message to reach Earth, another year for advice to return. The crew must be completely self-sufficient, capable of diagnosing/fixing any conceivable problem without outside help. The spacecraft needs not just spare parts, but manufacturing capability, knowledge base, skills, and tools. It becomes a self-contained industrial civilization, driving up mass, complexity, energy. From an engineering perspective, the longer the mission, the more likely something critical fails. Systems degrade from radiation, thermal cycling, micrometeoroids, fatigue. Where? We've built spacecraft lasting decades, Voyager, 45 plus years. But Voyager is simple: no crew, no life support. A crewed interstellar spacecraft would be orders of magnitude more complex, with thousands/millions of components needing to function perfectly for decades/centuries. Probability everything works that long is essentially zero. You need extensive redundancy, repair capabilities, ability to cannibalize systems, all adding mass, complexity, points of failure. Course correction and navigation. Space isn't empty. At high speeds, a collision with a dust grain carries enormous energy. At 0.1 C, a 1-gram particle hits like a small bomb. You need shielding, adds mass, sensors to detect obstacles, difficult with little warning time, ability to maneuver, requires propulsion/fuel reserves. Engineering challenges cascade. Now economics, everything described, energy, propulsion, shielding, life support, massive spacecraft, would cost staggering amounts. Conservative estimates, hundreds of billions to tens of trillions of dollars. Apollo cost about $280 billion, today's dollars, to reach the moon, 3 days away. An interstellar mission taking decades/centuries would cost orders of magnitude more, consuming a significant fraction of global GDP over many years. Why would any society invest? What's the return? Apollo happened due to Cold War competition. No comparable motivación exists. Scientific return would be substantial, but you could achieve much with robotic probes at a tiny fraction of the cost. Colonizing other star systems doesn't solve practical Earth problems. If we can't create sustainability here, why think we could light years away? The cost-benefit analysis doesn't work. Same resources could fund thousands of other projects with greater near-term benefits. Some argue interstellar travel as insurance, backing up humanity if Earth becomes uninhabitable. But this doesn't withstand scrutiny. First, Earth would have to become catastrophically damaged to be less habitable than interstellar space or an unknown exoplanet. Even post-apocalyptic Earth is more habitable than Mars, let alone an exoplanet. Second, if worried about existential risks, there are more cost-effective solutions. Asteroid detection/deflection, nuclear disarmament, climate mitigation, pandemic preparedness, robust food systems, shelters, all orders of magnitude cheaper. Third, an interstellar colony would depend on Earth for centuries/millennia until self-sufficient. If Earth collapsed, they might not survive without support. So they wouldn't serve as backup unless achieving complete self-sufficiency. The hardest part, requiring enormous resources. Interstellar travel doesn't solve problems, it creates them. It's not practical, but aspirational, motivated by romantic exploration rather than necessity. Aspirational endeavors costing trillions and taking centuries are hard to sustain in political/economic systems operating on shorter timescales. One more fundamental barrier: observational evidence. We've searched for extraterrestrial intelligence over 60 years, SETI, found nothing. No radio signals, no signs of advanced civilizations, no interstellar spacecraft, Dyson spheres, megastructures. This is the Fermi paradox. If intelligent life is common and interstellar travel feasible, where is everyone? One sobering answer: interstellar travel is simply not feasible. Not just difficult for us, but fundamentally impossible for any biological civilization constrained by physics. Perhaps every civilization remains confined to its star system. The galaxy might be full of civilizations, each trapped, able to see each other's stars but never visit. We're all prisoners. So when I say it's impossible for humanity to escape the solar system, I mean, not that we lack current technology, we do. Not that it's merely difficult/expensive. It is, but that the combination of physical laws, biological constraints, engineering requirements, and economic realities creates a barrier fundamentally insurmountable. We are trapped not by lack of imagination or technology, but by the universe's structure. The solar system is our home, our only permanent home. The sun is the center of the only neighborhood we'll ever inhabit. We can send robotic probes beyond, Voyager, but sending humans, creating viable colonies, truly escaping, these may remain forever beyond reach. But what does this mean for humanity's future? How do we think about our place given these constraints? Are there realistic loopholes? Understanding constraints is important, but so is understanding possibilities within them. So we've established distances are impossibly vast, energy requirements astronomical, biological constraints severe, economics non-existent. But before resigning to solar system confinement, let's explore proposed solutions, exotic physics, technological optimism, and why each, when examined, either doesn't work or pushes the problem elsewhere. Start with a popular sci-fi idea: cryogenic sleep/suspended animation. Put crew in hibernation, coast for centuries, wake at arrival. Solves boredom, reduces life support, crew doesn't age. Problem: we have no idea how to do this with humans. We can freeze cells, induce hypothermia temporarily, but preserving/reviving an entire human after decades/centuries? Science fiction, not science. Freezing causes ice crystals rupturing cells. We can't freeze/revive anything as complex as a mammal. Hibernation? Some mammals do, but human hibernation would need artificial induction/maintenance for far longer, preventing muscle/bone loss, brain damage. Need monitoring, absolute reliability. If system fails during decades-long journey, everyone dies. Radiation exposure continues. Shielding problem remains. And if something goes wrong with the ship, who fixes it? Need automated systems sophisticated enough for any repair or ability to wake crew reliably. Each layer of complexity creates new problems. Generation ships. Basic idea sound. Ship supports community over centuries. Multiple generations live/die aboard. But engineering challenges staggering. Fully closed ecosystem supporting thousands. Complete recycling, agriculture, industry, energy, functioning for centuries without external inputs. We've never built anything approaching this. Social/ethical dimensions. People born on ship never chose journey, confined to artificial environment, traveling toward destination they might never see. What if they decide not to continue? Mutiny, social collapse? Over centuries, values shift, purpose forgotten/rejected. Human history shows long-term projects abandoned, descendants not sharing ancestors' priorities. Expecting social cohesion/mission commitment over 10 to 50 generations through unpredictable dynamics seems extraordinarily optimistic. Genetic diversity problem. Need minimum effective population size, hundreds to thousands, to avoid inbreeding. Requires active genetic management, controlling reproduction, maintaining mixing, raising ethical questions about autonomy. Social engineering needed seems incompatible with free society, but without it, mission faces risks. Advanced propulsion. Fusion rockets could reach maybe 10% light speed. Proxima Centauri in 42 years, within human lifetime. Problem: we don't have them. Controlled fusion research over 70 years. Still no reactor producing net energy. Even if solved for Earth power, compact, reliable fusion rocket for decades in space is different challenge. Miniaturization, robustness, cooling in vacuum. Likely many decades after terrestrial fusion. Still, interstellar journeys take decades to nearest stars, centuries to distant, multi-generational endeavor. Antimatter propulsion, theoretically best, 100% mass-to-energy conversion, could reach greater than 50% light speed. Problem: no way to produce meaningful quantities. Total antimatter ever produced is nanograms. Producing a gram requires more energy than human civilization ever produced. Storage incredibly difficult. Magnetic/electric containment. Failure equals catastrophic annihilation. Harvesting from natural sources. Trace amounts in cosmic rays/radiation belts. Quantities tiny. Collection impractical. Firmly theoretical. No clear path to implementation. Exotic ideas. Laser sails. Plausible near-term. Project Starshot. Gram-scale probes to Alpha Centauri at 20% light speed, 20 years. Concept sound. Technology's challenging, but not impossible. But notice, tiny probes, one-way flyby, can't slow down, too small for humans/sophisticated equipment. Scaling to crewed? Vastly more difficult. Crewed spacecraft, mass millions times more. Need larger sail, more powerful lasers, gentler acceleration. Humans can't tolerate extreme G-forces, slowing at destination. Proposed solution. Magnetic sail interacting with interstellar medium to slow. Requires strong magnetic fields, large structures, depends on medium density. Another, laser stations at departure and arrival. Requires infrastructure at destination, chicken and egg. Realistically, laser sails might allow sophisticated robotic probes over coming century, giving scientific data/images. Sending humans this way faces probably insurmountable obstacles without far beyond technologies. Exotic physics, faster than light travel, wormholes, warp drives. Einstein's general relativity allows solutions like wormholes, shortcuts, Alcubierre drive, contract space ahead/expand behind, moving ship faster than light without accelerating through space. Problem: these require exotic matter with negative mass/energy density. We've never observed it, don't know how to create it. Quantum effects produce tiny amounts, Casimir effect, Hawking radiation. Far too small from macroscopic engineering. To create traversable wormhole/warp bubble, need enormous quantities of exotic matter, potentially Jupiter mass. If such matter exists and could be configured, maybe FTL possible. But many ifs. Most physicists deeply skeptical exotic matter in required quantities possible or engineering feasible. Also causality problem. FTL allows time travel paradoxes. Universe might have self-consistency mechanism preventing it. So exotic physics, while fascinating, doesn't provide realistic escape. Might be universe's laws prohibit interstellar travel, making galactic civilization possible. Speed of light isn't just technical limitation, fundamental feature shaping possibility. Another proposal, sending AI or uploaded consciousness instead of biological humans. No life support, no psychological problems, could shut down during journey. More radiation tolerant. Appealing, probably most plausible path to interstellar exploration if feasible. But if it's doing heavy lifting, No idea how to upload human consciousness. Don't fully understand consciousness if substrate independent. Would upload be you or copy? Technology, probably centuries away if achievable. Need connectome mapping at extreme resolution. Understand neural basis. Computational simulation, solve philosophical identity problem. Similarly, AI, we're getting better at narrow AI. Nowhere near artificial general intelligence, AGI. Thinking/reasoning/adapting like humans. Creating AI, making complex decisions, handling unforeseen situations, conducting science, maintaining itself over decades/centuries would require AGI substantially more advanced. Maybe eventually, but realistically at least a century away, possibly more. And would AI/upload want to spend centuries traveling? Not biological doesn't mean not bored or deciding mission not worthwhile. Philosophical question. If sending AIs/uploads instead of biological humans, is that humanity escaping? Or creating successors doing what we cannot? Biological human lineage remains trapped while technological descendants explore. Some find that satisfying, our legacy spreads. Others hollow, we're still stuck. Directed panspermia/von Neumann probes. Seed galaxy with life rather than traveling ourselves. Send frozen embryos, genetic material, self-replicating probes, creating life/intelligence at destiny. First, energy. Sun outputs 3.8 times 10 superscript 2 watts continuously. Earth receives 1.7 times 10 superscript 1 watts, 1 billionth total. Human civilization uses 18 terawatts, 1.8 times 10 superscript 1 superscript 3 watts, using 1/10,000th solar energy hitting Earth, which receives 1 billionth total. Energy available practically unlimited on human timescales. Harnessing tiny fraction could power civilization vastly larger/more energetic. Dyson sphere/swarm. Structure capturing significant fraction sun's output. Doesn't need solid shell, gravitationally unstable. Swarm of solar collectors in independent orbits. Building requires dismantling planets/asteroids for materials. Mercury. Mass 3.3 times 10 superscript 2 superscript 3 kg. Could capture substantial sun energy. Resources millions times current use. With that energy, support population of trillions, run massive computational systems, simulating virtual worlds, planetary engineering, terraforming Mars/Venus, melting ice moons, artificial space habitats, scientific research at unimaginable scales, particle accelerator size of planetary orbits, telescopes thousands km superscript 2 collecting area. Solar system material resources. Asteroid belt total mass 3 times 10 superscript 2 superscript 1 kg for percent moon mass. Enough to build thousands Earth mass structures if processed. Moons of Jupiter/Saturn. Vast water ice. Life support. Propellant construction. Outer solar system. Methane. Ammonia. Volatiles valuable for industry/life support. Space industrialization proficiency. Mining asteroids. Processing in zero-G, building orbit structures, create habitats more extensive than Earth's surface. O'Neill cylinders, rotating for Earth-like gravity, could house thousands/millions, total living area eventually exceeding Earth's many times over. Solar system resources could ultimately support population of trillions/quadrillions if utilizing space habitats. Not cramped survival. With sufficient energy, habitats comfortable, parks, forests, water bodies, cities, countryside, amenities of Earth but engineered deliberately. But time scales/practical constraints. Dyson spheres, asteroid mining, space habitats, trillion-person civilization require technological capabilities far beyond current. Would take centuries/millennia develop/build, even optimistic. Multi-century project, solar system, industrialization/expansion requiring sustained effort, enormous resources, continued technological progress. What we do depends on hard-to-predict factors, political stability, economic systems, social priorities, tech progress, environmental sustainability on Earth, etc. No guarantee successfully transitioning to solar civilization, even if physically possible. An even trillion-person civilization in space habitats still confined to tiny bubble around one star. Galaxy, 200 to 400 billion stars. Observable universe, 2 trillion galaxies. Utilizing one star's resources out of hundreds of billions. Living in tiny neighborhood of vast cosmos forever inaccessible. Confinement sense might not diminish just because prison larger might feel bars more acutely seeing more beyond. Profound psychological question. How maintain meaning/purpose as species permanently confined to single-star system? Cosmos vast/full of wonders observed but never explore? Throughout history, frontier always beckoned. Always somewhere new to go. Idea frontier permanently closes, reaching absolute limits of expansion, psychologically challenging. Some respond with denial, insist we'll find way, technology solve, barriers not real. Understand emotionally, but intellectually need honest about constraints. Wishful thinking doesn't change physics. Others respond with despair. If trapped, stars forever beyond reach, what's point? Why care long-term future confined to small universe corner? Cosmic nihilism unwarranted/dangerous. How I think, can't reach other stars doesn't diminish value what can do within solar system. Civilization mastering space, industrialization, building stable/sustainable presence throughout solar system. Preserving/studying life/consciousness arose on Earth. Extraordinary achievement, worthy effort/commitment. Analogy. Living on island, seeing other islands distant, but never reaching because ocean currents too strong, distances vast. Would island life meaningless? Fact can't visit other islands make yours worthless? No. Focus on understanding island, building good society, preserving ecosystems, creating art/culture/knowledge. Existence unreachable islands doesn't negate value inhabitable one. Same position, larger scale. Earth our island, solar system expanded island, nearby waters navigable. Other star systems distant islands see but never reach. Doesn't make island worthless/existence meaningless. Focus making most of what have rather than lamenting cannot have. But specific meaning interstellar expansion provides many imaginations. Need address if can find other ways, if impossible. For many, appeal about backup, ensuring humanity survives if Earth destroyed. Not all eggs one basket. Species resilient against existential risks. Understand motivation. True confined to one star system. Vulnerable system-wide catastrophes. Sun eventually dying. Nearby, supernova/gamma ray burst, rogue black hole passing through, or human-caused disasters spiraling out control. But most risks either so far future have enormous time address, sun red giant, 5 billion years, longer than complex life history on Earth, treating urgent requiring immediate solutions absurd, or so unlikely don't justify impossible expense interstellar colonization. Nearby supernovae/gamma ray bursts extremely unlikely relevant timescales. Rogue black holes even more unlikely. Existential risks in technical sense, not credible near-term threats. Risks should worry. Human-caused, nuclear war, bioengineered pandemics, runaway climate change, catastrophic technological failures, misaligned AI. Key. Interstellar colonization doesn't protect because could happen before establishing colonies or simultaneously across solar system, if interconnected. If can't manage risks on Earth, unlikely manage during extremely difficult establishing interstellar colonies. Solution to existential risk isn't escape, becoming wise enough manage technology safely, building robust systems surviving failures, creating social/political structures navigating long-term challenges. If develop that wisdom, don't need interstellar colonization for survival. If don't, interstellar colonization won't save, likely destroy ourselves before completing. So backup argument emotionally compelling, doesn't withstand scrutiny. Don't need for species survival relevant timescale. Worried near-term existential risks? More effective ways address than trying establish interstellar colonies. Another meaning source. Exploration/discovery. Humanity as pioneering species pushing unknown. Powerful motivation embedded culture/psychology. Idea, no new frontiers, seen everything reachable neighborhood, feels claustrophobic/limiting. But challenge assumption explored everything explorable solar system. Barely scratched surface. Humans to moon brief visits. Robotic probes to all planets limited reconnaissance. Not thorough exploration. Many solar system bodies more interesting/complex than initially thought. Europa, Jupiter moon global ocean beneath ice. More water than Earth's oceans combined. Isolated billions years, heated tidal forces potentially harboring life, evolved independently. Never explored ocean, never drilled through ice confirm exists, let alone sent submarines. Entire water world with own ecosystems unexplored. Titan, Saturn moon lakes/seas liquid methane/ethane, cloud/rain, river channels carve hydrocarbons, complex organic chemistry atmosphere. Most Earth-like body having atmosphere, liquid surface, active weather. One probe, Huygens, landed 90 minutes before batteries died. Extent exploration entire world exotic chemistry, potentially prebiotic conditions. Enceladus, Saturn moon geysers erupting South Pole, shooting water vapor/organic space from subsurface ocean. Numerous asteroids. Each unique world own geology/history. Venus, surface hellish, but upper atmosphere temperatures/pressures similar Earth surface, potentially harboring microbial life clouds. Solar system, not boring, well-X neighborhood. Diverse collection worlds, each unique, most barely studied, some potentially harboring life/conditions, teaching profound things chemistry/geology/climate/planets. Centuries exploration ahead, just within solar system, if commit. And actually feasible, unlike interstellar travel. Distances manageable. Months/years reach destinations, not decades/centuries. Communication delays tolerable, minutes/hours, not years. Energy requirements substantial, but achievable realistic technology. Could mount ambitious exploration programs, solar system budgets, billions/tens billions. Expensive, but not civilization-threatening like interstellar travel. So exploration motivation doesn't require interstellar travel. Plenty explore stellar neighborhood. Enough keep human curiosity engaged centuries. Difference robotic primarily, not human initially. Distances/travel times make human outer solar system exploration challenging though not impossible future tech. Point about consciousness role universe. One reason care, human expansion spreading consciousness/intelligence through universe. If consciousness rare, no evidence common. Something valuable spreading widely, experiencing/understanding more cosmos. But confined one star system, still do within reach. Thoroughly explore/understand solar system. Study universe telescopes/detectors, increasing sophistication. Develop theories/models explaining cosmic phenomena. Create art/culture inspired cosmos. Ensure at least tiny universe corner witnessed/understood/appreciated conscious beings. And if develop AI/upload consciousness, might send intelligence other star systems even if can't send biological humans. Earth-originated intelligence, spread galaxy even if biological humans confined. Explores descendants/creations rather than directly. Earth-originated intelligence exploring cosmos. Might resolution confinement. Remain here, create successors go where cannot. Successors carry knowledge, curiosity, perspective. Not human biological sense, but legacy, children metaphorical. Through them, humanity's reach extends beyond solar system, though humans never leave. Some satisfying, form immortality, impacting wider universe from confined position. Others hollow. Point if ourselves don't experience? Beings exploring, not us. No right answer. Matter gives meaning, consider worthwhile legacy. Deepest question raised apparent confinement. What means intelligent life universe if interstellar travel impossible everyone? If we can't, laws physics same everywhere, probably no one can. Galaxy full civilizations, each confined own star system, able detect others' radio signals, spectroscopic exoplanet atmospheres, technosignatures, but never visit. Explains Fermi paradox perfectly. Don't see evidence galaxy-spanning civilizations because impossible. Don't see interstellar spacecraft, / von Neumann probes, / Dyson swarms every star because resources required create / spread throughout galaxy prohibitive. Galaxy full isolated island civilizations, each doing best within star system. Looking out others' curiosity / longing. Forever separated distances / energy barriers no technology overcome. If true, profound implications future intelligence universe. No galactic federation, meeting civilizations, exchange knowledge / culture stars. Each civilization develops independently, dies independently, leaves legacy only detectable distant telescopes / radio receivers. Universe intelligent life, fragmented, isolated, unable form, cosmic community sci-fi imagines. Lonely cosmos picture. Might true. If so, need come terms rather than sustaining escape fantasies, distracting, making most actually have. One connection possible across interstellar distances, communication. Can't physically visit, can potentially detect signals, send signals. SETI decades, searching radio / laser pulses / technosignatures indicating other civilizations. So far nothing. Great silence. Puzzling if intelligent life common. But if most civilizations early stages comparable now, might not broadcasting strongly, not existed long enough signals reach us. Or deliberately quiet reasons don't understand. Or wrong search strategies looking wrong signals. If ever detect signal, transformative even without physical contact. No, not alone. Learn intelligence arise elsewhere persist long enough develop radio tech. Might learn science / technology / society. Communication light speed delays years / decades / centuries agonizingly slow. Conversation civilization 100 light years away. 200-year round-trip message times. Ask question, wait 2 centuries answer, everyone asking dead. But even slow delayed communication valuable. Exchange, scientific knowledge, cultural information, warnings, existential risks, insights building sustainable long-term civilizations. Over thousands / millions years, network communicating civilizations develop, each isolated physically, connected informationally, sharing products, isolated developments. Might best hope. Galaxy isolated civilizations, each developing independently star systems, occasionally contact electromagnetic signals, sharing knowledge / culture across space vastness. Not galactic civilization, but galactic conversation, slow, limited, meaningful. Perhaps enough. Perhaps value intelligence / consciousness universe, not physically spreading everywhere, but understanding, experiencing, communicating. Each civilization understands local environment thoroughly, contributes unique perspective collective knowledge, communicates, learns other civilizations listening. Together map universe, intellectually, even no single civilization explore physically. Where leaves us? Concluded interstellar travel likely impossible. Not difficult, genuinely impossible biological beings constrained physics / biology / economics. Solar system permanent home. Only home, extent reachable territory. Star-seen night forever beyond reach. Beautiful untouchable, marking cosmic prison boundaries. Not future, most imagined humanity expansion space. Not sci-fi, future galactic empires, interstellar commerce, meeting aliens face-to-face. More constrained, isolated, perhaps lonely future. But not hopeless. Within solar system, room grow, resources utilize, worlds explore, potential build civilization orders magnitude larger/capable exists Earth today. Possibility creating AI/upload consciousness might explore beyond reach behalf. Potential communicate civilizations, interstellar distances, creating network isolated connected intelligences galaxy. Most importantly, responsibility making most have rather than lamenting cannot have. Earth rare/precious world. Only place universe, no certain harbors complex life/consciousness. Preserving life, expanding consciousness solar system. Understanding universe observation/theory, creating knowledge/culture/beauty. Worthwhile goals, even never leave sun's gravitational embrace. Prison metaphor misleading. Yes, confined, but large/beautiful confinement, full possibilities barely begun explore. Sun not prison warden, source life, provider energy, center world literal/figurative. Bound not just physics, biology/necessity. Evolved here, adapted here, perhaps belong here. Stars not destiny. Inspiration, reminder universe vastness, perpetual source wonder/curiosity. Not home, never will be. Home here, stellar neighborhood around particular star bound, particular gravity, well chains physics, no wishful thinking break. Perhaps sooner accept, sooner focus building future actually possible rather than chasing future forever beyond grasp. Perhaps confinement, once accepted, becomes not limitation but focusing purpose. Here, have this, make most extraordinary civilization can within boundaries. Universe vast, small, trapped, but also conscious, intelligent, capable wonder/understanding/creation. Observe universe, even if can't fully explore. Understand cosmic principles, even if can't visit locations. Small, brilliant spark consciousness corner cosmos, witnessing/comprehending whole confined perspective. Might not grand destiny humans imagined, but destiny actually have. Enough. Has be enough because all going get. Making peace reality, first step building best possible future within constraints cannot escape. Solar system prison, sun cage. But perhaps if wise/committed enough, make cage home worth living, civilization worth building, legacy worth leaving whatever comes after. Challenge ahead. Not escaping confinement, thriving within. Not reaching stars, making most one star have. Not becoming galactic civilization, becoming best possible solar civilization, can be. Stars still beautiful, cosmos still inspire wonder, still look up night dream. But dreams tempered understanding, focused acceptance, made practical recognition true constraints/possibilities. Perhaps maturity species need see universe clearly, understand place honestly, build future realistically rather than fantastically. Staying here, making most here. Not defeat, wisdom.